All right, anyway. So last time we talked about working out, well, we worked out a lot of things, right? We worked out what the RMS speed is for a given system of molecules. We worked out average kinetic energy, and we worked out the overall thermal energy of a system. Now, one of the things that was really astonishing, actually, about that discussion was we had worked out what the speed is of something rather simple. I can't recall at the top of my head what that was, but it was like a room temperature thing, and I think we worked out that there was some particle that traveled at 1.4 kilometers per second, and that, when you see a number like that, you think, what is going on here? That is insanely fast. And I mentioned to you, like, well, it's fast, but doesn't travel really that far at that speed before it encounters another object and it experiences a collision. Well, let's work that out, actually. Let's work that out. So what I'm going to do is this. I'm going to make some assumptions here. Not terrible assumptions. But, we got a system of molecules. And it may be a little crude, not entirely crude, but we're going to assume those molecules are spheres, which is not a terrible approximation. And we'll say all these molecules are spheres of radius r. Okay? And so if two molecules are going to collide, that means their centers, okay, are going to be exactly a distance r apart, which means the entire extent of the two molecules would extend over a 2r distance, okay? And so if another molecule is going to encounter another molecule, then we think about a cylindrical space, a cylindrical volume. And the width of the volume is basically the minimum space in between two molecules. And the length, okay, or the height, you could say, whatever you want to say, of the cylinder is going to be the speed of the molecules times a little delta t. And the delta t is basically how often collisions take place. So we can figure out, how long, and that v delta t, by the way, is an incremental distance. So that becomes what we call the mean free path. It's the average distance a particle will travel before it encounters another particle. So how do we do that? Well, here's how we do it. So I'm going to draw some stuff overlaid here. Let me bring up the annotations to do that. But the idea is that imagine we have, I'll draw down here, I guess, a system that has n molecules in it, right? And those n molecules are going to exist in a container that has volume V. Now, when I take the ratio of n to V, what I'm getting is, how much space a single molecule will occupy on average. This would be molecules per volume. So I'm basically taking my entire volumetric space and I'm breaking it up into individual molecule spaces. Okay, those molecule spaces are these cylinders here, basically. All right, fine. Now, the cross-sectional area of this cylinder is 4 pi radius squared. Okay? Now, the 4 pi radius squared, that's the surface area of a sphere. And so that's the area that can get hit, basically. And then I have the VDT here, but I'm just going to label that as a distance. And in physics, for this particular application, we label this as a lambda. And the lambda is the mean free path. So that quantity right there is what we call the mean free path. And the idea is that this 4 pi r squared lambda is a volume, right? That's a volume. It's the cross-sectional area of the cylinder where collisions can take place. times the distance that's determined by how fast things are moving, and this is a density over here. And the idea is that if I consider this to be my volume, and I want to consider a certain number of molecules per volume, then guess what? This is going to be equal to 1, because one molecule will occupy a volume that is equal to this quantity I just defined here. And so then I can rearrange things, and I end up with a very similar statement. So if I rearrange stuff here, let me show you what I get. I get this quantity right here. So I solve for lambda here, and you can see in the equation, if I solve for lambda, the v goes in the top, and the n4 pi radius squared goes in the bottom. Okay, so that's all good. The only difference between the two, between the expression that I have here and the expression I derived, is this radical 2. Now, this goes beyond the scope of what we can do in Physics 211, but I will simply tell you that the additive radical 2 factor comes about when you consider that particles are moving around. They're not just stationary, that they move around, both particles that are going to have a collision move around. And so that slightly reduces the mean free path, because when things can move around, they don't have as much space as you would think they would. And so that's it. That's the expression. So we have this expression here for the mean free path. And let me go back here and clear this up a bit. So we have this lambda down here. Well, we have the lambda right there, but if we use the ideal gas law, well, I'll just keep this. If we use the ideal gas law, remember it's P, V, N, K, T. That's a version of the ideal gas law. If I take the ratio of V to N, then I can see that this actually ends up to be K, T, 4 pi radical 2. I'm getting the hang of this little pad here. What's up, buddy? Over what? P, right? 4, yeah. And so that's another expression, and both work just fine. Just depends on what you have. But I just use the ideal gas law to get this different one here. And then if you notice right here, part of the definition of the mean free path is, it's a certain incremental distance. So how fast are the particles moving? This would be the, VRMS times the mean free time by which things hit. So guess what the mean free time is? It's the same thing. In fact, we actually use a tau. You'll see me use a tau. Tau is kind of meant as a mean free time in collisions. I use it in 120. I can't remember if any of you had 120, but it's in 120. And if I do that, you get the exact same expression with an extra factor in the denominator, which is the VRMS speed. This P is pressure, just to be clear. Pressure. All right? So you got these two different expressions. Do I got my... Well, anyway, you didn't don't peek. You didn't see that. I messed up. Okay, I got a million chords and things, and it's hard to manage all this stuff. All right, anyway, so, oh my gosh, if there's a letter in the chat, if I check there and there's a letter in the chat, I'm going to lose it. You two wisecrackers, don't do it yet. I'm not there. Oh my goodness. Smart Alex. All right, let's get to it. All right, let's move on then. All right, the temperature. The temperature of a rigid container of oxygen gas, O2, is lowered from 300 Celsius to 0 Celsius. As a result, the mean free path of oxygen molecules will do what? What will happen? It's B. Why? If I go back to this expression here, the mean free path doesn't have a temperature in it. They say, well, Professor McGovern, didn't you just tell me about this other expression that does have temperature in it? And I will say that, yeah, I did do that. But hello, there's a pressure term in here, and do you know what's going on with pressure? No, you don't. We don't know what happens with the pressure here. We just lowered the temperature. Do other things change? Probably. Okay? But we got a rigid container. So here's the thing. You know what? This is the beauty of this stuff, right? You got to look at that language. You got to start really critically thinking for yourself here. Temperature changes. Okay, fine. Will that make other things change? Probably. But let's go back and look at these two expressions here. It's a rigid container, right? So is the volume going to change in a rigid container? No. No, it will not. Will the amount of molecules change in a rigid container? All right, then we go to the other expression. Well, I mean, that settles it, really. But you go down here and say, oh, I got a function of, does the temperature change? Yes, it did. Does the pressure change? I mean, yeah, it did, right? Because what's the ideal gas law? Let's look at the ideal gas law, right? Let's look at ideal gas law. P, V, N, R, T. Did N change? No. Did V change? No. Did the universe change? No. Did temperature change? Yes. So guess what? Pressure had to change. All right. But we go back to this expression here. And the only thing that's difficult about this stuff is any difficult. It's just a million equations. There's a million equations. You just got to find the right one. And that's your job. And I'll help you out a little bit. But you know what? Okay. Excellent work. I will try not to ruin the answer ahead of time, though. Let's do a problem. Let's get right into it. All right, what did I do with my problems here? Here we go. Buckle up. Here we go. We want to know what the mean free path of a nitrogen molecule. If you didn't know, diatomic, triple bonds for a nitrogen molecule. Nitrogen really likes itself. Triple bond is nuts. Anyway, nitrogen molecule, diatomic. Now, check out what I'm saying right here. Okay, this is not clear until right now. A diatomic molecule. Okay, we are going to make a general statement in this course. A diatomic molecule will, on average, have a radius of 1 times 10 to the minus 10 meters, which is a tenth of a nanometer. Remember that number, okay? Because it's going to come up a lot. And it's something that the book kind of mentions. I will kind of mention, but it's something that you really need to know. I mean, you can dig through Google and come up with the stuff on your own, but you're not going to get anything that's too dramatically different. All right. We have the pressure. We have the room temperature. Now, I have two different expressions for my mean free path. One that involves volume and number of molecules, and one that involves temperature and pressure. Which one do I use? Well, you use the one where you have the most information. I don't have the volume here. I don't have the number of molecules, but I do have the temperature, and I do have the pressure. So I know where I'm going with this. I'm using my KT over P expression. Put all the numbers in. You got the Boltzmann constant, 1.38 times 10 to the 23rd. Put your temperature in. Are you going to use Celsius? You better not use Celsius. Better not use Celsius. Okay? You're going to use kelvins, right? Okay. 4 radical 2 pi 1 times 10 to the 10 squared. That's your radius of the molecule. Put in your pressure. Got to be pascals. Don't you try to put those ATMs in there. Don't think so. 2.2 times 10 to the minus 7, which is 220 nanometers. That's the mean pre-path. What is 20 centigrade? That's like room temperature in some areas, right? What is that? It's like 60-something, isn't it? Am I dumb here? Celsius, 20, right? 20C to F. 68. What did I say? Did I say 60? I think I said 68. Wow. All right, 68. That's a nice room. That's a comfortable room. I like those kind of rooms. 68. Ooh, that's comfortable. And that's the room temperature. So that's normal. Atmosphere, well, you know, that's the atmosphere. And so guess what? In the room you're sitting in right now, right? The room you're in right now, you got a bunch of nitrogen around you. You got like 78% nitrogen around you. And what is it doing? It's flying around the room like crazy, but guess what? Every 220 nanoseconds, on average, it hits another molecule. It hits another molecule, right? Every 220 nanometers. Did I say nanoseconds? Sorry, I didn't mean that. Nanometers. Every 220 nanometers, it hits another molecule. That's a tiny space. That's a really tiny space, actually. Okay, now I also want to find out the mean time of collisions because, okay, fine. It travels that distance, but how quick is that? Well, you take your lambda and you divide it by the RMS speed. We already did the RMS speed. That was last class. RMS speed, there's two forms of it, but I'm going with the one that has molar mass because I know how to do the molar mass for the nitrogen molecule. 3RT over the molar mass. Hydrogen is, again, diatomic molecule. Each nitrogen is 14 grams per mole, so we got 28 grams per mole. Got to put in kilograms. 3 times 8.3, which is the gas law constant, times the temperature of the room, which is 550 meters per second. Half of a kilometer per second. That's what's happened. That is what is hitting your head right now. You got nitrogen molecules. I mean, it's probably a little warmer than 20 Celsius. My house right now is around 25. I don't put my thermostats too low, honestly. And but that's what's happening right now. There are nitrogen molecules hitting your head at half a kilometer per second. And the ones that hit your head only traveled about 220 nanometers. So anyway, with that speed, with this mean 3 path, that means you're getting collisions. A lot of collisions in a fraction of a nanosecond. Fraction of a nanosecond, right? That's crazy, right? Isn't that nuts? I mean, it's inconsequential ultimately, but and we could also work out. I didn't work this out here, but how many? I mean, you got to take the surface area of your head. We got to look at the density of air. We can figure out how many nitrogen molecules are bouncing around on your head. Your head would explode with this information if it were not for all the collisions keeping your brain intact. All right. I think I need to lay off a little bit of the coffee here. My coffee game is a little too strong today, to be honest. All right, let's move on. This is a great problem. I love this problem. It's just so interesting, right? I mean, it's so real. You're sitting there. You got nitrogen going off your head here. It's cool. It's a great problem. I really like it, actually. All right. This is an in-class activity, which means we're going to take a little break here. I know we're only half an hour in. Okay, but I like you to practice stuff. So I'm going to give you about 5 to 8 minutes. I don't know what we're doing here, but I want you to work this out on your own. Spend a little time, think about this, scribble some stuff. It's not for a grade or anything, right? Just see if you can do this problem right now based on what you learned. What is the mean free time between collisions for a monatomic gas with a molar mass of 40 grams per mole at STP? So the diameter of the molecule would be 4 times 10 to the minus 10. All right, try to work it out. Try to work it out. Not too challenging, but I'm going to give you about a little more than 5 minutes. Okay. We want the mean time, right? Got to calculate your lambda first. Calculate your VRMS. So let's go do the VRMS first. So that's fun. I'm going to go with the 3RT over molar mass one. We're given the molar mass, so why not, right? STP means we're dealing with 0 Celsius or 273 Kelvin. So we got 3 times our 8.3, 273 divided by 0.040 kilograms per mole. And we end up with an RMS speed of around 412 ... All right, I can put that into my mean time equation. I'm going to want to use the one with the KTP in it because I know my temperature and I know my pressure. It's a good one to go with. So I put all my numbers in, and we end up with a number that is 0.127 nanoseconds. That's small. So a particle only moves about a tenth of a nanosecond before it hits another particle, and then it moves, and then another tenth of a nanosecond. So the air around you is busy. Very busy. All right, so if you attempted that and you got it right, thumbs up. Good job. Let's move on. Now, so guess what we talked about before? We talked about the total kinetic energy of a thermal system. When we did that, however, that system was a monatomic gas. And what did we end up with? We ended up with the following. That the total capital... Oh, come on. Why don't you want to draw... Oh, here we go. The total kinetic translational energy... Why did it do that? It was 3/2 at... I'm having a little difficult time here, apparently. Let's try this with the annotations instead. I think I'm pushing some button on here. You gotta understand, I'm an old man. I don't get this technology. All you Twitter kids and Instagram kids, I don't get what you're doing with all your hashtags and whatever. Anyway, the total translational energy we worked out to be 3/2 nRT. And I didn't tell you, I mean, I kind of told you, but that is for a monatomic gas. Now, the 3 comes from somewhere. If you go back to the derivation, the 3 comes about because you worked out what the energy would be for a single direction, and then when we incorporated the other 2 directions, so we say I worked out things in X. I said, well, you can do things in Y, you can do things in Z. It doesn't really change anything. It just adds additional layers to the speed. And the 3 comes about because we have 3 dimensions. Well, we have this neat little theorem, actually, that's involved in all this stuff called the Equipartition theorem. And it says that the thermal energy of a system at its core is 1/2 nRT times the number of degrees of freedom. And what does that mean? When we talk about degrees of freedom, okay, I'm going to give energy to a system. Okay, I'm going to add a heat. Okay, so I got a box, I got a gas in there, and we're going to start, transferring energy into the box. Where does it go? Well, it goes into different modes of energy. For something like a monatomic gas, that energy is going to be imparted into 3 degrees of freedom. 3 ways that gas can take that energy and do something with it. And for a simple monatomic gas, that means speed in the X, Y, and Z directions. And that's why we originally ended up with a 3/2 nRT for our kinetic translational energy. But you could have more degrees of freedom. And that happens when you have potential energies involved. Let's delve into that. Let's get into it. Let me ask you a question first, though. we have a mass on a spring here. Let's assume we have a frictionless surface here. I'm going to draw the mass out, and I'm going to let it go. And it goes back and forth, back and forth, back and forth. I'm going to ask you, how many degrees of freedom does this system have? Okay, AKA, how many different ways can energy be imparted into the system? B's, B, a lot of B's, and it is B actually. There's two modes of energy here. The potential energy due to elastic potential and the fact that it oscillates in the x direction. Okay, so it really comes down to this. Kinetic energy, how many dimensions are we working with here? X, Y, Z, what are we doing with? Well, we got only X. 1 degree of freedom there. And then there's potential energies. And in this case, we only have one potential energy. It's spring, and it's in one direction, so there you go. 2. Okay. We're going to go over this a couple more times. All right. So, when we talk about the thermal energy of a system, and I already explained this to you, but now we're just going to more formally connect ideas here. The thermal energy of a particular system here, and which is related to basically specific heat, is that for a monatomic gas, only monatomic gas, the thermal energy is 3/2 nRT, or you can go 3/2 nKT if you want to do it that way, but that's a monatomic gas. If you want to talk about, energy transfers, you can put a delta E thermal, and that would be a delta T here. All right, simple enough. Now, way back, this was probably in the first lecture, actually. It's the first lecture? I think so. We had a different expression for the change in thermal energy. Now, what you learned actually was a different expression. It looked like this. Let me annotate this. You actually learned a slightly different expression, an expression that you're actually much more familiar with. And that expression was Q, mass, specific heat, delta T. But if you really go back to that first lecture and you dig through the slides a bit, I kind of mentioned something for like, a few seconds. I said, well, if you don't want to work with mass, you can work with moles, which is what we have here, moles. And then your specific heat becomes a specific heat by moles. And so this is an alternative expression, okay, that can take the place of this one if you have other information, like you have moles instead of having mass, okay? Well, if you're dealing with a gas, okay, and we equate these two expressions together, look at these two. Well, the delta T is here, the N is here, and so we end up with an expression that the molar specific heat for a monatomic gas is always the same thing. Is it helium? That's it. If somehow you have just hydrogen gas, which is also monatomic, if you got neon, that's monatomic, then the molar specific heat, okay, that would be in joules per mole per Kelvin instead of joules per kilogram per Kelvin, because this C right here, joules per kilogram per Kelvin. But if you have joules per mole per Kelvin, then the CV is very predictable. It's 3/2 R. It's always, no, you got to remember this. Monatomic gas, and if we impart heat to the monatomic gas, how do we calculate the temperature differences? Well, we do it through this expression in the middle here, and we know what CV is, 3/2 R. Okay, fantastic. Clear this stuff out, moving on. Now, we don't always have diatomic molecules. You don't have any diatomic molecules. What we have, so we don't have monatomic, is what I mean, right? The atmosphere is diatomic. Diatomic nitrogen, diatomic oxygen. So what's going on there? Very similar, except we have additional degrees of freedom. At standard room temperatures, when you put energy into, say, for example, the air around you, yes, you could increase the kinetic energy in the x, y, and z directions. But when you impart energy at, again, standard room temperatures, there are 2 additional degrees of freedom that can show up. All right? And those are associated with rotational energy. Okay? You can take a molecule. Do I have... Gotta have something around me here. Well, let me just use my empty club soda bottle. I have no idea why this is here, but how can you rotate this thing? Well, you can rotate it like this. Okay? And that's a unique rotation. You could also rotate it like this. That's a unique rotation. You could also rotate it like this, but there's no change in the system if something rotates like this. And it really doesn't require any energy to do that. It's basically tumbling. This is tumbling, and this is spinning. Okay? And that means there's 2 more degrees of freedom. And that's true as you heat up the air. Yeah, it will bounce around faster, but it also has the ability to start incorporating rotational potential energies. And so it has 5 degrees of freedom. 3 for translational, 2 for rotational. If you really heat things up, and I'll show you that in a moment here, then you can get atoms to vibrate. And that creates a spring potential, and that can add even more to it, actually. We'll get there. Don't worry, we'll get there. So, anyway, the point of all of this is this. If you have a diatomic molecule, you don't use 3/2. You use 5/2. And your CV is not 3/2, it's 5/2. Just take note of what gas you're working with here. Question for you. You have a mole of an ideal monatomic gas. You have a mole of diatomic gas. It's hot enough that things are going to rotate. Okay? Initially, both gases are at room temperature. If the same amount of heat flows into each gas, which gas will undergo the greatest increase in temperature? Okay, so we just got monatomic, diatomic, throw heat into them. What's going to experience the greater energy transition? Greater amount of energy. So I'll give you about 30 seconds, put a letter in chat there. A lot of A's. I'm liking it. I'm liking the A's. What time is it? Some of you got B's. Not B's. Guess what? If you're going to put energy into the system, where is it going to go for monatomic gas? It's going to go into translational energy. If you put that heat into a diatomic gas, where's that going to go? Some goes to translational energy. Some goes to rotational. Ultimately, the specific heat of the monatomic gas is lower, and so when you impart heat, you can get it to a much higher temperature. The answer is A. Okay, great. It's the same logic we had before. A smaller specific heat can take more heat and raise temperatures. Okay? Something with a larger specific heat is stubborn, right? It's stubborn. Right? That's what we said. So, now, check this out. This is from a different textbook, but trust me, your textbook probably has identical values because this stuff is set in stone pretty much. Got a couple monatomic gases here. Helium, argon. What's their CV values? 12.847. What's that? It's 3/2 R. What about diatomic gases? Hydrogen, nitrogen, carbon monoxide, oxygen. Very, very similar values. What are those values? 5/2 C. Polyatomic, it gets a little complicated. Yeah, you get rotations. You actually get another dimension of rotation so that your degrees of freedom actually now jump to 6. But then rotations get really complicated. And so it's kind of a weird... So once you get to polyatomic, it becomes a little more complicated. because you start to get to 6 degrees of freedom, and then you go above, and then you got rotational things. I'm sorry, vibrational things, and that becomes a little bit more difficult. And as you can see here, we got a big spread of values among standard polyatomic things, and it really comes down to the fact that vibrational things start to play a role, and that just makes everything very complicated because now you got to think about moments of inertia and all kinds of crazy stuff that go with that. Still fun, not as easy though. That's the issue. Here's what I was talking about here. When you're very cold, everything's translational energy. But at some point, when you get to like room temperatures, rotational effects take play. And so your diatomic gases start to look different. And then if you get really hot, again, really hot, you're going to get to temperatures that you don't find on Earth. Temperatures for stars, vibrational plays a very large role, and then you can have higher values. In this class, though, almost always, it's 3/2 R or 5/2 R. You just got to take note of whether it's monatomic or diatomic. I mean, there may be some problems we have to actually find the degrees of freedom, and then anything's fair game there. But if that's not the focus of the solution, then you got to be mindful of whether you have diatomic, monatomic, things like that. Okay. So we got, okay, question for you here. Letter in chat. Molar heat capacity at constant volume. Now, don't worry about this constant volume language at the moment. I'm putting constant volume in here, and I'll just tell you one really quick thing about it, and we're going to delve into this in a later chapter. The reason why I'm saying constant volume is this. When things are at constant volume, there is no work performed by the system or on the system. Because when you add or take away heat, right, you change the thermal energy of your system. But what else can do that? Work can do it. And we're not talking about work right now. That's for the next chapter. Right now, we're not concerned with work. That's the first law of thermodynamics. That's next chapter. So when I say constant volume, it's my little disclaimer. No work is being performed in the gas. Because if you have constant volume, you can't do work on a gas. Okay? Work has to do with distances. If things are at constant volume, no distances are changing, yada, yada, yada. Purely heat transfer. All right, anyway. Molar heat capacity at constant volume with diatomic hydrogen is 5/2 R, diatomic. But it's only 3/2 R at 50K. What's up with that? 50K is pretty darn cold. Letter in chat, please. All right, this is quick. Because this question's like, hey, did you listen to what I said 30 seconds ago? Ha-ha. Y'all did. C. All right, so if you're cold enough, rotational aspects don't play a major role. So if the rotation's not a factor, then it acts like a monatomic gas. But as soon as you get to room temperature, which is around 300 Kelvin, things change. All right, let's do it. Let's keep going. I'm loving this. How much heat does it take to increase the temperature of 1.8 moles of an ideal gas by 50 Kelvin near room temperature if the gas is held at constant volume and is diatomic? How does the answer change if the gas is monatomic? All right, let's analyze everything I'm saying here. How much heat does it take? Well, we're talking about NCV delta T. All right, let me get my pen out here. Okay, how much heat does it take? Okay. Uh-oh. Got to do my annotations here. I apologize. What time do we got here? Ooh, we got a whole hour left. Lucky us. Everybody's like, are you kidding me? I want out. All right, anyway. How much heat does it take, right? NCV delta T. That's the heat. We got the moles. Do we have the CV? You bet we do, because this is a diatomic gas, and we are near room temperature. So that means we're going to include the degrees of freedom for rotation. So our CV value is 5/2 R. That's what this value is. All right, so how much heat? Well, let me just jump to my slide, my other slide, because I already worked it out. I don't want to reinvent the wheel here. 5/2 R for a diatomic gas, 3/2 R for a monatomic gas. I got my NCV delta T. Work out the diatomic stuff, 1.8 moles, 5/2 R. 50 is the change in temperature, 1,870 joules. Great. Monatomic gas, 3/2 R. The same amount of temperature difference doesn't need as much heat. We just talked about that, 1,120. All right. Great problem. It's actually not a great problem. It's kind of too easy. But if you understand it, then you probably actually get quite a bit of what's going on here. All right, so let's talk about this one here. Calculate the specific heat capacity at constant volume. So that means, again, I'm going to annotate stuff. Calculate the specific heat at constant volume. So our CV is unknown. Assuming water vapor, assuming that the nonlinear triatomic molecule has 3 translational and 3 rotational degrees of freedom. What? Well, that's 6. Okay, so that's 6 degrees of freedom. Okay. The molar mass of water is 8 grams per mole. I know that. Compared to the actual specific heat capacity of water vapor at low pressure, which is around 20,000 joules per kilogram per Kelvin, and consider whether vibrational emotional energy needs to be taken into consideration. Well, we know how to do this. We know how to do this. You take 6 times 1/2 R. That's what we do. Okay? That's 3R. What's 3R? 3, 8.31 is what? Well, why am I doing this? I already worked on my slide here. Let's just jump to my slide because I already got it. Oh my goodness. Stop freaking out. Let's just get to it then. All right, so 6 degrees of freedom. CV is 6 times 1/2 R. That's 3R. Okay. Now, that's my molar specific heat. But look what I was asked to compare to. I was asked to compare to the standard specific heat that involves mass. So I got to convert this. Okay, so if I convert this, I take my value for C and my 3R here, but I got to divide that by the molar mass. So right here, you can see what the relationship is. If you want to take your CV values and convert it into ones with kilograms in it, well, you got to divide by the molar mass. The moles drop out, the kilograms go in there. So if I do that here, I find that my specific heat that involves mass is 1380 joules per kilogram per Kelvin. Well, I'm asked to compare that to 2000. Well, they're not anywhere close to each other, are they? Those are very different from each other. So here's what I'm going to do. I'm going to go back to my calculation, and I'm going to put an N here. Now, I thought my N was 6. We were wrong. It was not 6. So I put an N in here, and I go through the same calculation. Sorry about that. I don't know what that's doing there. And I work out that my N value is around 8.6, which is telling me that I have approximately 2 to 3 extra degrees of freedom. Well, where do those come from? Well, you already got your translational taken care of. You already got your rotational taken care of. Well, it's got to be some vibrational things. And so apparently, the vibrational aspects of water is very important. Is very important, actually. And that's one of the reasons why water is stubborn. It's why the specific heat of water is so high. It's stubborn when you throw heat into it. Yeah, things start bouncing around, but then things start to do little dances, and they spin around, and they vibrate, and they go back and forth. And that takes a lot of energy away from the system, where normally that would go into the increase in the temperature. That's what's happening here. So this is a big reason why water is stubborn. Okay, this is a great problem. Great problem, to be honest. It's a great problem. All right. So we're going to take another, we're halfway through, so we're going to take a 10-minute break here. Okay, just to, get up, move around. But you can work on this problem or think about this problem in 10 minutes of time. Let's do that. We got rigid containers, constant volume, hold n moles of an ideal gas. One is diatomic, one is monatomic. It takes 300 joules to increase the temperature of the hydrogen by this amount. How much is it going to take to heat up the neon? Okay, so the hydrogen's diatomic. It has a greater specific heat. Okay, and so how many degrees will the same amount of heat raise? Well, it will be more, right? Monatomic has a lower specific heat, and so the same amount of energy should make it go up, but how much? All right, so we're going to take a 10-minute break right now. What we're doing here. All right, so the only difference here really is this. Remember, diatomic 5/2, monatomic 3/2. So we equate the two delta Qs. We have an N, 5/2 R, delta T. We have an N, 3/2 R, delta T. R's drop out, moles drop out, and we end up with that the neon is going to experience a greater temperature difference by a factor of about 1.6, 5/3, 1.6. And, we put the temperature difference of, 1.5 that we know that hydrogen's doing. And we increase that by a factor of 1.6, we get 5.83. Right? So it's just a matter of managing the 5/2 and the 3/2. We equate the heats to each other, and from there we get our increase in temperature. So it's easier to heat neon because neon doesn't have a bond with itself where there can be rotational things. Fantastic. Let us move on. Okay. Now, we're talking a lot about gases right now. Okay? The reason why we're talking about gases is because things are generally much simpler for gases, and you can really nail down a lot of the concepts for gases before you delve into more difficult territory. And some of that difficult territory is when you get to solids and liquids, because then things get complicated. Okay? But if you think about what solids are like, because you can make some really simple, not assumptions, but you can make some really simplifications. That's really the word. And, when we look at a standard solid structure, it's some kind of lattice where you kind of have this three-dimensional grid. And this picture illustrates that very nicely. When you have a solid, you have all your molecules very close to each other. And they have their own thermal motions. They're bouncing around. But ultimately, when they bounce around, they're interacting with their neighbors. And when it comes to a solid that has a significant amount of temperature, high temperature, there are 6 degrees of freedom. Because nothing can rotate. So there's no rotational things, right? Nothing can rotate in the solid. But you have the little bumping around that can be in 3 dimensions. And you have spring potentials that are also in 3 dimensions, up, down, left, right, forward, back. And so there are 6 degrees of freedom in a lot of hot solids. And so the thermal energy for a solid is going to be 3 times nRT. Okay? And we see this in solids that when the temperatures get significant, depends on each one. Some have resilience. Diamond is resilient because it's so beautiful. And that's not the reason why it's resilient. It's because the bonds, as you may know, diamond is a strong compound. It's because the carbon bonds are very, very good, put it that way. And so it's diamond's resilient. But it's not like lead and aluminum. It's more malleable. When things are more malleable, things have more freedom to sort of shift around. And we find that for things like room temperatures, like lead, aluminum almost, behave very closely to the prediction that things are going to be at 3R. Now, there's a name for it here, Dulong-Petit prediction. It's just the prediction that Solids, when they get hot enough, approach this 3R value because of the way that they are. So anyway, beyond that, we can't say really much more about solids without getting really technical. And liquids, forget liquids. Liquids are way more complicated, actually. All right, so let's switch to a seemingly unrelated topic. It's not totally unrelated, but we're just trying to get through the rest of this chapter here. And this addresses the issue we had before. We worked out RMS speeds for molecules. Well, it's a root mean square, which means it's a type of an average. In reality, if you look at a particular substance, it has a distribution of speeds. Now, in 211, we don't have those tools. We don't have the means to figure out, how this distribution looks, which I'm sure you're okay with because I'm not throwing any insane math at you right now. Okay. But this is an example, okay, of how those distributions look. This is, I believe, nitrogen at, it says right here, nitrogen at 20C. Right? And so this is the distribution of speeds for different molecules. There is a most probable speed, which is right here. There's the RMS speed. There's an average speed. There's actually a lot of different concepts here. But you can see the distribution. There's a peak somewhere where the vast majority of speeds lie, but things can be a little larger, things can be a little smaller, and that's just randomness. Statistical randomness, that's it. Well, we do have a way to express this, and it's called the Maxwell-Boltzmann distribution function. We indicate this by an F of V, and it sort of looks like this. This is speed versus the frequency of those speeds. So this function here is a partition function, normalized actually, and so when you add up all the speeds here you get a 1, but it gives you a spread like a histogram in such a way. And generally speaking, as you heat objects up, the spread increases, okay, and less molecules are actually at the average. When you lower the temperatures, things kind of tighten up. You have less of a spread, and a lot of molecules kind of fit right in the middle there. That's kind of the nature of this. Now, there is an expression for this, which I guess I'm going to, I'm going to show you this, and I'm going to go back to the last slide because this is kind of a natural transition here. Here's our equation here. It's pretty gnarly, I will admit, but this is a distribution function. And at its core, it's a function of velocity. So, there's a lot of symbols here. Most of them are constants. What this function is, it's a, think about this, x squared to the e to the negative x power. That's what the functions are at their core, which is what these things look like. Okay, and any coefficients that are there alter the peak, alter the slopiness. Can I use that word? I just did. I'm going to use it. Slopiness of the function. I don't know. Slopiness. I like that word. It kind of sounds fun. Slopiness. I'm just laying back on a Saturday, just getting my slopiness on. I don't know. It just sounds comfortable. It sounds relaxing. I'm just going to go with it. But anyway, this equation here is an early equation, and we're obviously we're not going to delve into the details behind this, but I'd like you to know, mathematically speaking, x squared e to the minus x. There's some fun stuff there, some fun stuff. Remember, you calculus people, you want to integrate this? You guys know what you got to do? How do you integrate this function? Because that's interesting. If you integrate this, guess what? If I integrate this over all velocities, I should end up with a value of 1, right? Anybody know the method? How do you integrate x squared e to the minus x? I don't know. I don't know. It's probably parts. Every time you have a polynomial times an exponential, it's parts. But now that I think about it, this is an x squared up here. I think that complicates things. Now I'm questioning myself here. I'm questioning myself. Who am I? I don't know, but I think it's a parts thing. Yeah, I'm pretty sure it's a parts thing. The x squared now is tripping me up here, but that just comes out as an x, and that's just part of the polynomial. Whatever. We're not doing that. I'm sorry, we're not doing it though. Okay. But guess what I'm gonna do? Yep. After I'm done here, I'm gonna do it. I've been up since, well, you know how long we've been up for. Do I want to sit there and do integration by parts? No, but my mind will say, too bad. Thirst for knowledge, you know? Anyway. All right, so in the distribution here, the thing we can do with the function, we can do a lot of really interesting things with that function, right? We do some calculus with the function. What does it mean to integrate the function? Well, I already explained. If you integrate the entire function, which, you know, I mean, I'm not going to do that. Guess who's going to do that? Wolfram Alpha is going to do that, right? So anyway, I'm also just going to throw in the Wolfram Alpha and see what it says. I mean, it'll take me a minute, but still. Wolfram Alpha would tell us what it is, and that will give us, if you integrate over the entire breadth of the function, you get a value of 1. If you integrate within an interval of speeds, then you get something very interesting. You get the fraction of molecules that have those particular speeds. What about this most probable velocity, right up here? Uh-oh. If I want to know what that most probable velocity is, what do you think we're going to do? How do I figure out this value? I don't want to figure out the value at the top here. I want to figure out what x value gives me this peak here. Anybody know? What kind of calculus kung fu are you going to do on this thing to figure that out? Anybody remember? How do you figure out a value like that? What's the most probable value up here? What's this peak? What's this maximum? Ooh, I said it. Maximum. You want maximums? What are you doing? I'm seeing something in the chat. There you go. Take the derivative, set equal to 0. Solve. Guess what we're going to do today? We're going to do it. Now, we're going to do it. Anyway, so while I'm not going to derive the function for you, we can still have a lot of fun with it. Question for you here, a little calculus knowledge. I kind of already ruined this. I kind of already told you what's going on here, but, you know, give me your opinion anyway. We have a quantity of gas contained in molecules, has a speed distribution function of f sub v, Boltzmann function. How many molecules of this gas have speeds between? All right, so only 3. Don't be shy, people. Don't be shy. Everybody's saying D. You know what? I'm liking D a lot. Why? Here's what you do. You take that distribution function. You integrate it from 0 to V2. What does that tell you? It tells you the percentage of speeds up to the value of V2. Then you integrate from 0 to V1. You get the percentage of values up to V1. When you subtract the integrals, you get the percentage in the interval, and that always corresponds to a normalized value of 1. So if one particle is doing that, you multiply by n, and you get n number of particles. There you go. We want to find the most probable speed of the Maxwell-Boltzmann distribution function. Well, I already spoiled it for you. We're taking the derivative, we're setting it equal to 0, and we're solving for our value. Now, I'm not going to attempt to do that on my trackpad thing here because it already looks like I'm got the skills of a 4th grader when I try to write. Actually, I don't. 4th graders can write pretty well. Let's go with maybe a 1st grader. Yeah, I think that's probably better. But we got df dv set equal to 0. The function, I've simplified it, and this is a good idea to simplify, but it's I chose that, you know, if you look at the equation, there's a bunch of stuff in the front which matches stuff in the numerator in the index of the exponential. So I'm going to call that a, right? And then let's take the derivative of it. And so you got a chain rule thing going on here. It's all good. 2v times your exponential plus, leave the v squared alone, take the derivative of the exponential, which returns the same function, chain rule stuff, minus 2av. Clean it up. The exponentials drop out of the equation. We end up with something that's really nice and elegant, a 1a delta v. I'm going to go ahead and put what the a is from what I extracted out of the equation. And you just got to compare this expression right here. Oh, what did I do? What did I do? I just destroyed my computer. No, I didn't destroy the computer. I just stopped the screen share. Okay, I thought my computer died for a minute. Okay. You compare this with the function I have in my slides, and you can see what the a is. But anyway, you get this value here. This is interesting. Because what was the RMS speed? 3 kT over m. This is 2 kT over m. So it's a little less. The most probable speed is not the root mean square speed. Now, the root mean square speed, just to be clear, was designed as an approximation. It was just a simplification of the derivation that didn't require us to invoke anything crazy. And it's not 100% accurate, right? Because it's not 2 kT over m. It's 3 kT over m. But it's close. It is very close. And so what we find here is it is a good approximation. It is a good approximation, right? Not perfect, but it's pretty darn good, actually. All right, let's move on. How are we doing on time? All right, I think we're good on time. For carbon dioxide gas. Oh, I think we're basically done. Are we basically done? Aw, we're basically done. Aw. I want my day to end this quickly. I'm so sorry, everybody. For carbon dioxide gas with a molar mass of 44 grams per mole at 300 Celsius room temperature, what's the most probable speed, average speed, and RMS speed? This is great. We're comparing the 3 different types of speeds that we've worked out so far. We're going to see how these things look. So let's do it. Let me jump to my slide here. All right. The most probable speed, radical, 2 kT over m, or you can swap it out, 2 RT over m. Either one is good. Well, I mean, lecture's over when I'm done. The time on the class is basically a muzzle for me. Don't make them stay past 5:20. But if we're done a little early, we're done a little early. I mean, I'll just be honest with you. You know, these classes might run a little short because, you know, I mean, I'm giving you the same lecture I would give you in person. But the thing is when I'm in person, you know, I sit there and I write things on the board. And that takes a lot of time, actually. And, you know, now that we're doing things online, I'm not going to do that because it's not convenient to do it. So I craft a lot of the stuff ahead of time using things I already have or things I make up. And so what happens is class times are going to be a little shorter, just naturally because we're not face-to-face. All right, anyway. Okay, here we go. 2 kT over m is the most probable speed. Okay. The average speed. You know what I'm thinking about? I don't think I covered average speed. I don't think I actually covered it. That's nuts. Well, I'll show you how you do it if you want to know. It's not a fun calculation, but you take that integration, take that function there, and yeah, it's actually not a fun. That's why I didn't show it. It's not a fun calculation. But what you do is you take the distribution function, and you multiply it by a v, and you integrate it. And when you multiply any function by its arguments, and you integrate it, you're working on an average. And so, yeah, I'm not doing that because it's a bit of a beast, right? And it's x cubed times e to the minus x, and we're taking the integral of that, and that's not a friendly thing. But turns out, when you work that out, the average speed is 8 over pi times those quantities. And 8 over pi is what? 2 point something, right? 8 over pi is about 2.5. So it's right in the middle. And then, of course, the RMSP we've worked out. So we got a factor of 2 here, 2.5, 3. So you get a nice distribution here. Ultimately, the one that is really important is the most probable value, because that's the peak of the distribution curve. But for a lot of what we do in the class, we're going to stick with VRMS because it's a good approximation, and it's tied with a lot of other things that we do mathematically speaking. So I'll just say that. All right, what's at the bottom here? I have some note. Note. Yeah, we already know that. I don't need to tell myself that. I already know it. All right, we got one last problem here. Let's just jump into it. Now, yeah, I got a few things to say at the end of class, by the way, but water vapor, molar mass, 10 grams per mole at 400 Kelvin. Calculate same thing. Well, this was because it was in class activity. Anyway, same numbers, same things. Just remember these equations. These are the speeds. Again, that's crazy, right? Water vapor, that's fast, man, right? Fast. All right, so, excuse me, I'm going to dish out some reminders to you. We don't meet on Monday, right? You have an exam. It goes live at the beginning of the day on Monday. Get all of Monday, get all of Tuesday to do it. A little bit of multiple choice, a bunch of free response questions. You write up the solutions, you take pictures, you upload them into the Canvas assignment. That's going to be the exam. Let's see what else here. There's a couple other things. There's 2 homeworks due on Monday. Okay, so the homework from Monday and the homework from today. Give me a little bit of time to do that, because I actually have a class that I teach later. I have another class after this. And depending on how long it takes me to set things up for the class and how much stuff I have to do for my other classes, I may or may not be able to put up the homework by today. If I don't put up today, it'll be up first thing in the morning. So the study guide for the exam is put on my webpage there. And what I did is simply this. I went through an old test bank of mine. Yeah. We went through a test bank of mine, and old test bank. And I just pulled out questions that were based on things we have done in this class that I think you ought to know how to do based on what we learned here. So the study guide is just basically a series of questions that you ought to know how to do. Again, no indication of what the test might be like at all. Yeah, when you do the test, though, you got to submit pictures of some kind, whether you actually printed out things and hand wrote stuff and took pictures, or whether you have an iPad or a Surface or something and you just write things on there. I don't care how it is. I really don't care how you do it. Ultimately, by the end of Tuesday, I want to go into the Canvas assignment. I want to see picture formats of some kind, PDFs or whatever, that are in there. So I think that's all I have to say. I have office hours tomorrow, 9:30 to 11. If you want to chat. Also on Monday, we're not going to meet, but I'll be on office hours. I'll be on during class if you want to ask questions about things. But I think that's all I got to talk about for today. So throw your name in the chat, and